Okay, first let's recall that the magnetic field at a distance r from a long straight, a current running along a long straight conductor is 2k prime I over r. Okay, there's your magnetic field. Now, we assume a loop and a magnetic field, a current running into the board. So we have a loop of radius A with the current running into the board, and we're asked what's the integral of the magnetic field around this loop having radius A. We can easily make the argument that we don't really need to do an integration to find this. If we have a delta S increment here, and that was kind of poorly written. I crowded it with what we have up here. I should have done it elsewhere. But as I say, I'm not batting 100,000% today. Well, let's just say, okay, here's our delta S. The delta S vector is here parallel or tangent to this loop at some point. The magnetic field, if the current is into the board, then thumb in the direction of the current, right hand tells us the magnetic field is surrounding the wire in this direction. So we have the magnetic field here. The magnetic field is in the same direction as delta S. Now, when I say the same direction, it's along the same line as delta S. It would actually be in the opposite direction here. So the dot product of B with delta S is going to be negative the product of magnitude of B times magnitude of delta S. But that's not particularly important for what we're talking about right here. Okay. So this integral is going to have, for every segment, it's going to have magnitude of B delta S. So that, as in the example we did before, where we calculated the magnitude of the field at the central point, we can simply add up all the B delta S contributions around the circle. And that's going to give us a result of magnitude B times 2 pi A. Now, the question is, in what direction do we integrate? Well, we integrate in the counterclockwise direction. And then the B in this case would be negative because the current is going in the negative direction relative to the loop. Okay, so we'd have a negative here, and I don't want to get into the details of that. I'll take care of that later. You want to be careful about those things, but let's just get the concept here. So the magnitude of the B delta S, and I should probably go ahead to make this correct. I'm saying the magnitude of B delta S is B times 2 pi A. The magnetic field here is 2k prime I over R. So R in this case equals A, the R being the distance from the field to the point at which we, from the current to the point at which we calculate the field. And we get this expression very clearly. We get the 2 pi A times the field 2k prime I divided by A. Again, the negative is taken care of by the sign of the current. And we end up then, just multiply this up, 4k prime I, and that's equal to mu naught I, since mu naught is equal to 4 pi k prime. Okay, so that's going to be the result. Now, in general, the integral of magnetic field dot ds is 4 pi k prime times the enclosed current, the current enclosed inside the loop. Okay, C is the boundary of the loop, and I enclosed is all the current that passes through the region bounded by that boundary. Now, you know from multivariable calculus that this could be any region, and this is related to the integral theorems, more specifically in this case the Stokes theorem, and we'll draw those connections later. But that's how we prove that this works not just for the current in the center of the loop, in other words a loop that surrounds the conductor at constant distance, but any old loop that we want to make around this conductor. Okay, and any old loop is going to include all the currents that pass through. And we're going to see how that works out here in just a minute. Okay, so anyhow, we have this general conclusion that the line integral of B dot ds around any closed curve that bounds the surface is going to be this. Okay, generalizes this result. And again, those results are generalized using the integral theorems of multivariable calculus. The next situation we wanted to look at on today's document is a situation where you have 1,000 wires with 0.3 amps of current running in each, and those wires are running and equally spaced between the x-axis and the y equals 1 meter plane. Okay, so they're equally spaced over a distance of 1 meter. They all run in the x direction, and each carries some current I. So we can see if there are 1,000 of them that span 1 meter, that they're separated by a millimeter. Okay, now each of these separated by a millimeter. Well, I can't really draw all 1,000 of them. As I said in class, I drew most of them here, but I think I left out a few. Okay, so here's our y-axis. Now looking at this thing head on, we have these currents coming out of the y-axis, coming at us in the x direction. We have a z direction up here, so let's go ahead and label that. It might make things a little more clear. And naturally, I didn't draw all of the all of the wires here, or all of the currents. The currents are coming out of the wire at equal spacing over 1 meter. There are 1,000 of them, not, how many do I have here, 10 or 11, 12. But what we want to do now is we want to consider another line integral over a rectangular region that looks like this. And the specifics of the region are that it runs from 0.4 meters to 0.6 meters, according to the document, and from 1 millimeter below the y-axis, so very close to these wires, okay, and up to very great distance away. I said 1,000 meters. So here's our loop. Okay, well, enlarging the loop and enlarging just this portion of the picture, and we see we've got a bunch of currents coming out at us. Actually, between 0.4 meters and 0.6 meters, we have 200 of these things, and I've only drawn 5 here. I only drew 5. I might have drawn a few more if we'd had better resolution over the video, but you can see it here. Now, I want to consider the line integral of the magnetic field around this loop. And it turns out that over 3 of these sides of the rectangle, over 3 segments of this boundary, the total contribution to the line integral is going to be 0. Now, that leaves only, it's this one, and this one. Basically, this is really far away, so the field is negligible. And if it's not negligible, just make the thing longer. Make the thing as long as you like until the current or the magnetic field along here at this distance, which is 1,000 meters in the statement of the problem, is 0. Make it 1,000 kilometers. Make it a parsec, whatever you want. You can make this far enough away that this the contribution of the line integral here is going to be 0. Okay. The line integral here and the line integral here, by a symmetry argument that we'll look at later, are equal. This contribution is equal and opposite to this contribution. Leaving just this segment here, and we want to analyze the line integral over this part of the boundary, because that's the whole line integral, and of course that line integral is going to have a field such that the entire integral of B dot ds, which is equal to 4 pi k prime times the enclosed current here being 60 amps, which we easily calculate over here, is all due to this. And we're going to make an argument that says, well, the magnetic field is in the same direction as the line and is constant, okay, or very nearly constant. Okay, so again, the enclosed current is just the 200 wires that are enclosed between 0.4 and 0.6 meters multiplied by the 0.3 amps, which is 60 amps. So the total line integral is 4 pi k prime times 60 amps. And since we're going to end up with a uniform magnetic field here, the line integral is going to be equal to just the 0.2 meters multiplied by the magnetic field. And that's going to be equal to this, and we're going to then be able to easily solve for the magnetic field. So we're going to go ahead and do that in the next clip. And I'll just add, this is called Ampere's law. I never referred to it by name in the discussion, but that's what we call it. This is Ampere's law. Now we're going to apply Ampere's law to a situation that I've sketched here. We'll do that in the next clip.